Hi, mathematicians. We're going to spend a little bit more time talking about linear independence. And so let's go ahead and look at our auxiliary equations with repeated roots. So I know you've already solved these, but now that we've talked a little bit more, I don't even care about the initial condition for this because that's not the point. Now that we've talked a little bit more about linear independence, I want to talk about why this is happening, right? So the auxiliary equation to this, as you know, will have a repeated root of -2. R1 and R2 equals -2. And so the solution to this, I don't know, what am I going to call it? I'll call it my milk. Y milk of t equals C1e to the -2t plus C2, I'm going to write a space, e to, normally, right, we just put c's in front, and then we did the thing, right, the roots, and each one got its own guy. But in this equation, when it's repeated, we are making you put another t here. What is that t for? Why is this here? To make them what? Linearly independent, right? Otherwise, it's the same solution, right? There's no point. Okay, and so that's why we're throwing that extra t in. Okay, so from there, let's go ahead and let's define what the Wronskian is. So the Wronskian is a more systematic way to figure out if solutions are linearly independent or not. And so let's get a little math speak here for a minute. I'm looking for the official Wronskian words. Okay, here we go. So the Wronskian, if y1 of t and y2 of t are any two solutions to the differential equation that are linearly no. Oh, what are you doing, Beth? What are you doing? Okay. You are reading the wrong thing. Put your glasses on. That was defining linear independence. There was nothing wrong with what I was writing down. It just wasn't what I was going for right now. Okay, back to the Wronskian. Okay, the Wronskian is two solutions, y1 of t and y2 of t are two solutions to the differential equation, the diff EQ, on and if the equality y1 tau, I think that's tau, y2 prime, a tau, this is basically we're going to create a matrix, which some of you might not have had matrix algebra, and that's fine, we'll get through it. We're going to create a matrix, and then we're going to find the determinant. And if it equals 0 at any point, then y1 and y2 are linearly dependent. Okay, so if this holds, that this equals 0 at any point, then y1 and y2 are linearly dependent. Okay. Okay, so let's do just a little bit of practice doing a Wronskian. So let's verify that t squared and t to the third are linearly independent using the Wronskian. Okay, so the first thing you're going to do is we're going to go ahead and set up our matrix with y1 of t and y2 t. Then below them, you're going to do the primes of each one. Okay, so this is going to be 2t, this is going to be 3t squared. Okay, so that's how you set up this matrix. And then we're going to find what's called the determinant. So if you've already done matrix algebra, you'll know that the determinant is this times this minus this times this. So it's going to be t squared times 3t squared minus 2t times t cubed. And we're checking to see, does this equal 0 ever? Right? And so if we go ahead and do this, what do we get? We get a 3t to the fourth minus 2t to the fourth. Does that equal 0 ever? Actually, equals 0, equals 0, equals 0 never. Right? 1 never equals 0. So therefore, they are linearly independent. Okay, and so let me just show how this matches up with that like weird weird definition I showed earlier. Let me see if I can do this. Okay. Right, so this was the definition we wrote down earlier, right? So we have, this is just my y of t, basically, right? And then this is, what is this? This is the derivative of the other guy, right? So we have, I'm going to write it in terms of t, because you guys will like that better. So that's y1 of t times y2 prime of t minus y2 of t times y1 prime of t. Do you see that? I guess these are switched. That's fine. It doesn't matter, right? But do you see that? I hope so. Okay, let's see. Do I have another example I can throw out there real quick out of my hat? Let's take one of the ones from before that we did the C method. Okay, let's go ahead and check and see if cosine t is that linear independent of sine of t. So what do? Let's use the Wronskian. Using the Wronskian. Okay, and so let's go ahead and my y, so let's set up our matrix and we'll get our cosine of t and then we'll get our sine. Does it matter who you put here and who you put here? It doesn't. Just make sure that the derivative of this guy is here and the derivative of this guy is here. Okay, but it doesn't really matter who you decide is y1 and y2. And so what is our derivative of cosine? Oh, I forgot, right? So if you've forgotten what the derivative of these magnificent creatures are, and I look at this, I know that the derivative of sine, this is positive, this is all above at this point, right? It goes negative, this goes below. I know the derivative of sine is cosine t. Then what is the derivative of cosine t? Well, it actually has to be negative sine t. And so let's go ahead and find the determinant. This is going to be a cosine t times cosine t minus sine t times a negative sine t, so that becomes a positive. I don't know, I'm doing weird stuff with my parentheses, don't worry about it. So this becomes cosine squared t plus sine squared t. That equals 1, right? It never equals 0. Therefore, linearly independent. Okay? All right, so knowing the Wronskian and understanding linear independence is, one of the student learning outcomes of the course.